well, as we shall see, some non-Newtonian dynamics and stuff like that. His PhD supervisor is Hongsheng Zhao, who we have had talking to us before on this subject. Very interesting stuff. So, Indranil studied maths and natural sciences at Cambridge before specialising in astrophysics. And he's also worked on a summer project involving force balances in ice shells, which is something that interests me a great deal. And he now works on the mysterious forces balancing galaxies. So he's going to talk about that. He's one of 3 winners of a prize visit to USA, and tonight he'll be expanding on, or expounding I should say, on the work that he's done.
Was that before Trump got in?
Yes. So I'll hand you over to Indranil to give us a look at some of the forces involved in galaxies and some of the mysteries of gravity. Okay, thank you, Andromeda.
No, that's fine. Thank you. So I'm going to be talking about trying to understand galaxies without dark matter. So hopefully the cover slide for my talk, the meaning of it will become clearer as we progress tonight. So first of all, when we observe galaxies, you should be able to predict how quickly they rotate as a function of distance using the Newtonian gravity, the inverse square law, which kind of works very well in the solar system. The problem is that the observations which fall up here show a major discrepancy with the theoretical calculation. So just to give an idea, outer planets in the solar system are rotating slower than inner ones, but the outer parts of the galaxy rotate at the same speed as the inner parts. So what's called a flat rotation curve. So that's very weird. One possibility is that galaxies are surrounded by large halos of dark matter. So the idea there is that galaxies look like this. The thing is though, we don't have any direct evidence for the dark matter, which is just an artist's conception. So actually galaxies look like this, right? So there may be invisible dark matter here, but we don't know for sure. I'm going to be arguing that there actually isn't any. So just to give an idea, how we're going to show this is divide like the acceleration you actually observe by what you kind of predict applying Newton's theory to the visible mass. And on here you're going to have like the predicted acceleration. So if you can't predict the dynamics, the acceleration from the visible mass, if there's just no proper correlation, then that means that there has to be something else, dark matter, right? Assuming the laws of physics stay the same. So, on the other hand, if you could predict the dynamics from the visible mass, then you don't really need invisible mass, right? You could just use what you see. The thing is, so this is what we actually see, that the ratio between observations and predictions follows this very unique correlation. What this means is that you can predict the dynamics from the visible mass, and therefore the data suggests you don't need to add in extra complications like dark matter. So the thing is though, obviously you need to modify gravity if you're going to go down that route. The reason is that this line, although there is a well-defined relation, it's not a flat line at 1, which is what would happen for existing theory was working. So you have to have a new law of gravity. So first of all, to give you an idea of how Newtonian gravity works, in the outer parts of galaxies you can treat them as a point mass, and the equation is very simple, that the gravitational acceleration is equal to the centripetal acceleration. You need to keep something moving around the circle. Okay. So this leads to the v decreasing with r. Now this equation, we know that it doesn't always work, right? So for example, if v is very high, close to the speed of light, then we know that there's going to be special relativistic corrections. Right? So it's not always exactly correct. Now, but I haven't said whether quantum mechanics might affect the result as well. So these are the two major breakthroughs since the time of Newton coming up with this theory, right? So what could that do about this particular problem? So first of all, Newtonian gravity and the general theory of relativity that it approximates, the basic assumption is that you can kind of define positions and velocities of objects arbitrarily, precisely. Okay, so you could say exactly what something is. Now, in the real world, that's not actually possible because of quantum effects. Still, you can assume that possible and try and think, well, is that a reasonable thing to assume? So, the basic picture you want to have in mind is that space-time, if there's like a mass here, it kind of looks like this, kind of curved by the matter. The typical picture people have of general relativity with like a trampoline. You approximate it like this. Okay, so this is what a general relativity solution for the problem might look like. So that might actually look reasonable. Now, what happens if you look at like a much smaller mass or much further away where the accelerations are much smaller? Then it's curved much less, but you're still stuck with the same procedure, right? That you approximate it as if it's totally smooth. The thing is, here you might be missing a big part of the picture because, for example, if there was energy in all these corrugations, you might miss all that. Whereas here, it might have been okay-ish. So what that means is that this is probably not a good approximation. In other words, that if the acceleration is very small, like ignoring the quantum effect is probably not such a good idea. So, another way of looking at it is that on a large scale, space-time kind of looks flat, smooth, right? But if you kind of if you want to know the dynamics of particles to within like, I don't know, 10 to the minus 11 meters per second squared, you kind of really look at it under a microscope, sort of. At that level, there might be additional quantum fluctuations. Not very much, but at that level of precision, they might make some difference, right? The idea here, alluded to earlier, is that basically empty space, because it's not actually just totally flat, because it has all these corrugations because of quantum effects, essentially it has a small but non-zero minimum energy. So it's like if you have a particle like on a pendulum, it can't just have the minimum possible energy, it has to be a certain amount above that because of quantum effects, it has to be kind of oscillating a little bit. So you can think of empty space as having something like that. There's vacuum energy density, right? We can't really calculate how much this should be very precisely. So I'm not going to get into arguments about why this has a particular value. What I will say is that you can observe it. It's causing the universe to accelerate apart. Okay? And this is what it should do. The global, large-scale global effect of space being filled with the uniform energy density should be an acceleration, which we observe. So people have won a Nobel Prize for this observation. What you can do then is use the rate of acceleration of the universe to kind of calculate this rho vacuum. Now that leads to an interesting, very quick calculation you can do. So this is the energy density you have in a gravitational field, according to Newtonian mechanics. This must be known like centuries ago. This vacuum energy density we've recently been able to measure the last 10 years how much it is. And that tells you that these two things are comparable at a very low acceleration, about 10 to the minus 9, 10 to the minus 10 meters per second square. Okay, so what you want to think about is basically the energy density is kind of supposed to scale linearly with the square of the gravitational field. Classically, the result is like this, but we know that if there wasn't actually any gravity, that there should still be some vacuum energy. So maybe the total is kind of like this, but we don't really know exactly how they add. For example, if they add in quadrature rather than linearly or something. So the main message you want to have is that in these circumstances, very low accelerations, we really don't know what should happen. 'Cause obviously this is a quantum effect, this is a classical effect, you don't really know whether you can just add them up like that. And even if you could, that might still affect the dynamics. So what happens to these low accelerations? Basically, I could tell you if I knew how quantum gravity works, but seeing as we don't, what this means is that I don't know what will happen there. One thing is for sure though, probably it will work differently to the prediction of a classical theory. So a classical theory like general relativity will probably not work in these circumstances. That means the Newtonian gravity is probably not going to work. More importantly, the smaller the acceleration, the bigger the failure is going to be. Right? Whereas at very high accelerations, it probably start working again. So the thing is, if you actually see in the real world an acceleration-dependent discrepancy with your classical theory, then it's probably a signature of quantum effects, because it's acceleration you could think of as energy density instead. It's sort of analogous to saying if a gas deviates more and more from classical theory as the temperature gets lower, then that's a sign of quantum effects, which is true. That's why gases deviate from the ideal gas law at low temperatures, fundamentally. Right. So, indeed, as I've shown you earlier, we do observe exactly such a thing. More importantly, like not only is there an acceleration-dependent discrepancy with the classical theory, but the onset is about where we predicted it. So just to give an idea, the solar system acceleration scale, so this is logarithmic, the solar system is way over there somewhere, at about like 10 to the minus 2 meters per second square. So it's 10 to the minus 9, and you can see that's basically where the onset of the discrepancy is, within like a factor of 5 or 6, roughly speaking. This is this is what I was saying. Now, what happens if you plot parameters other than like acceleration on the x-axis? So if you plot like distance from the galaxy center, where you collect each data point, versus like the acceleration discrepancy at that point, well, then there isn't like a proper correlation. But if you plot acceleration on the x-axis, there's a strong correlation. So here, the important thing is you can actually see sort of tracks of individual galaxies. Now, obviously, if there was a fundamental theory, you shouldn't be able to tell apart like galaxies like that on a figure showing something fundamental. So the fact that you can means that the distance will be relevant, which is good, because you shouldn't really have theories depending on how far you are from the galaxy's center. Like, that's not really physically very meaningful, right? Whereas acceleration is something you kind of measure locally. So this makes some sense physically that the acceleration could be important. So the latest observational data is kind of like this, where you show the predicted acceleration against the actually observed one. This is the line of equality. You can see like things start to deviate kind of what we expect based on the quantum mechanical argument, and then in fact the residuals are extremely small. It's gotten even tighter over time. Now this naturally leads us on to the idea of modified Newtonian dynamics, which essentially says that Newtonian gravity is off by some factor, depending on acceleration. So this, by the way, people suggested this before the discovery of dark energy. So the way I presented it is designed to be logical rather than how it was discovered. The idea behind this is to basically boost gravity by a certain factor depending on the acceleration, but it's an empirical thing, right? Which is required because we don't know what happens in quantum gravity, so we need to leave some gap in the theory to adjust to fit observations. So it's kind of like leaving gaps in a periodic table for things that you don't know what they'll be like, but you're sure they have to kind of exist. So for example, we know that quantum gravity has to exist because quantum mechanics and gravity exist and they have to work together consistently, but we don't know exactly how strong it will be in particular circumstances. So the basics of MOND are governed basically by this equation, saying that the gravity times mu is the Newtonian gravitational prediction, So what happens at high accelerations is nothing. They're the same. G and Gn are the same. But at low accelerations, you set mu to be equal to its argument. So you can see that what will happen is that G will equal square root of G and A naught. So yeah, you basically kind of square root the Newtonian gravitational field, which the main thing so far is that it leads to 1 by r force law, which is kind of designed to make the galaxy rotation curves like flatten out in the outer parts. But the theory was designed to do that, so that's not very impressive. The main thing is the scaling with square root of m, which you'll see in a minute what that does. So if you apply the centripetal force balance argument like to the new law of gravity, then you get the v to be the fourth root of the mass times a constant. Yeah. So if you then look at the actual data and plot like the baryonic or the normal mass on here against like the speed at which the rotation curve of a galaxy flatlines, then you see a really tight correlation over sort of a factor of maybe 100,000 in mass. Yeah. So the other thing is that the color coding is corresponding to whether the stars are, whether the galaxies are star dominated or gas dominated. Star dominated up here and gas dominated down here. They fall on the same relation, which is quite important, as I'll come to in a sec. So in classical gravity, what would happen is more like this dashed line. Basically, you try and fit some cosmological paradigm to how much dark matter there should be. The thing is, there should be basically 5 times as much dark matter as normal, which if you kind of apply it in a straightforward way, you just get this line. So really not very good. What does cause this decrease in the baryonic mass? So I'm phrasing it that way because the dark matter is supposed to be dominant in the standard model. So right now I'm trying to show you why this can't work in the standard model. So in the standard model, you can lose a lot of your baryons, but because they still make up only a small fraction of the mass, the rotation curve probably wouldn't change much. So people who work on this in the context of the standard model, so most astronomers, what they will need to do is try and explain this drop in the baryonic mass. So how can it have been lost from galaxies, right? So there are ways to do that, right? It's not totally impossible. You can have things like supernovae, but the thing is, you only need a few in some of the smaller galaxies, okay, down here. So this kind of thing will depend on the environment of the galaxy and how exactly it's formed stars, which obviously is going to be some amount of randomness to this. What this means is that you shouldn't be able to get such a tight correlation of how much you've dropped with VF. So sometimes you might drop by a little bit and sometimes by a lot more. Basically the amount of scatter here is really too small to kind of understand. Yeah, I mean, so that's one thing. Now the other thing is that so far I've talked about the flat line level of the rotation curve. If you look at the rest of it, you see some very interesting features. So this is the rotation curve of a galaxy, and this is the Newtonian prediction. Observations are here. The dark matter will add for you like a smooth dark matter halo around the galaxy, right? Yeah. But the dark matter can't radiate off energy and kind of cool, so it can't like clump into dense like planets and stars. It'll just be a smooth addition of dark matter. What MOND will do is multiply the Newtonian rotation curve by some factor, which kind of gets larger with radius. So it'll get like this purple curve, which you can see is actually work much better. Basically this dip in the actual rotation curve corresponds to a real dip in like the surface density of matter at like that radius. There isn't like any good reason why that kind of dip should also exist in the dark matter. It will just get washed out by the fast random motions of the dark matter, which is thought to be like a hot gas essentially. So this is slightly weird, like how...
Interesting correlation.
Yeah. This is called Renzo's rule, so there's other galaxies where it appears as well. Well, this is the most notorious example. I think there's something similar in the Milky Way actually. but it's a bit harder to see. This is a field equation governing the modified Newtonian dynamics, and this is a mu function that we usually use. So, there's more examples like this you can see at Stacey McGaw's web pages on MOND. Recently people have found that some galaxies should be dominated by dark matter in the standard model, because of that, you can just kind of simulate the dark matter only and not worry about the baryons too much. And we can do dark matter only simulations quite well. That should tell you how quickly the galaxy is rotating as a function of distance, like the internal forces everywhere. The baryons will, there are going to be some baryons, they have to act as traces, but even if you sort of all blow them all up, it shouldn't matter very much for the rotation curve, because they make up only a very small fraction of the mass. So these kind of galaxies should be a good test of the theory. We'll just show you what actually happens with this. So this publication looked at like kind of 4 typical examples, and what it found, so the predictions are like this green or this colored band corresponding to some uncertainties of what the baryons exactly do. And you can see that in the case it kind of worked well, but in a lot of these cases it hasn't worked very well. Which is quite weird, right? So I'll just show you how MOND fares with these objects. So if I show this one first, so in MOND it's kind of worked more or less perfectly. So this was the most problematic case for lambda CDM. But if I show you some of the other ones, like this one again it worked. This one more or less alright. This one I think there might have been a bit of an issue with, but not very much. Systematic offsets like this can be accounted for by the inclination of the galaxy not being exactly what you think, because the outer parts are tilted relative to the inner parts or something. Warping like that can happen at a few degrees, which is all we needed here. So MOND has kind of worked in all of the cases. It hasn't failed by very much. So another thing that people did is look at what happens with dark matter. So some astronomers got like a rotation curve of a galaxy and like the image, a color image to see, so they could try and predict the rotation curve, and then they got like the actual rotation curve. So you get basically in MOND what happened is they couldn't really fit the data very well, whereas in Newtonian gravity plus dark matter they seem to have gotten a perfect fit. So this might look like very bad for MOND. So then people ask like, well, which real galaxy is this? Like, so they could kind of observe it again or something. So it wasn't a real galaxy. So what had happened is it was an experiment where you give astronomers like a rotation curve and the image of the wrong galaxy and see if they can still fit it. So the lesson here is that dark matter can fit just about anything. Whereas MOND actually can't, it can only fit real galaxies apparently. That's because of the large amount of freedom with the invisible dark matter, which could be just about anywhere, right? So the thing that is kind of adjusted in MOND a little bit is the mass to light ratio. So you only really see the light. So you have a bit of flexibility here. The important thing is that the color is necessary to tell you what sort of stars the galaxy has and what the ratio is between the mass and the luminosity. So you can kind of do that based on a local solar neighbor where you can kind of see like everything pretty much. You can kind of predict the mass to light ratio if you know like how stars work and what color the galaxy has. So then, obviously this has to kind of work with MOND essentially. So what's shown here is kind of the mass to light ratio that MOND needs in the blue band and in the near infrared band against measure of color, and the lines show you the what you expect. So this is the expected mass to light ratio as a function of this particular color. And the dashed lines show you the level of scatter you expect. given that all stars are the same, if they have a different metallicity, they might have a different mass to light ratio. And you see that MOND kind of gets right the slope, which is already quite weird. And also it gets right like the absolute normalization. So you could argue the theory is being tweaked a little bit to get that to happen. But weirdly, it even got the amount of scatter right. So the amount of scatter you see about like this relation is kind of how much scatter you'd expect there to be, given like subtle differences between stars in their composition, for example. So the message is that the mass-to-light ratios that you need in MOND, they can be adjusted to fit the data, but we have independent constraints, and we know that what MOND theorists tell you they need are reasonable numbers to be having. Recently, people have kind of tried this. So far, I've talked about disk galaxies, rotating ones. What about like ellipticals? So before, people used to only have these data like out here, what are called integral field unit observations, like kind of look at the stars. But it's a bit difficult because you can't really tell the balance between rotation and kind of random motions in an elliptical very well. So it's a bit hard to do properly. Recently, people managed to get like a small fraction of the ellipticals which have a rotating gas disk. They have a small amount of gas which settles itself into a disk by like friction, and they got like all the data points like down here. And even more recently, apparently, they managed to get data further out in like X-rays. I think you have like a hot halo of gas around the elliptical, which you can see in X-rays, and you can measure the temperature and pressure and use hydrostatic balance to work out how strong gravity is. And they got like the results here. So what's shown in blue is kind of the relation between observed acceleration and predicted one for the spirals. So what you see is that the actual acceleration is tightly correlated with what you expect from the baryons, from the normal matter in ellipticals, in basically the same way as in spirals. So what this is meaning, so it makes good sense in modified Newtonian dynamics, but in the standard model, what this means is that basically ellipticals have to kind of work in the same way as spirals in terms of how much baryons are thrown out and things like this, which makes no sense at all because obviously they're extremely different. They're about as different as you could get, right? This is very puzzling in the standard model. So recently I've been doing some work on the local group of galaxies, so like the Milky Way and Andromeda, so I'll kind of talk about that a little bit more. In the standard model, you basically have the local group would look kind of like this. So it's sort of dark matter, like kind of all over the place. And there's some concentrations, and at the center of this one would kind of sit the Milky Way in theory. This is kind of how it actually looks like. So much more empty. There's actually not really much evidence for all this dark matter here. You could probably tell here that there should be some satellites of the Milky Way, quite a lot, and they should all be kind of all over the sky. In the real world, there's two problems. First of all, there aren't that many satellites. So this is what's called a missing satellite problem. So most satellites have to stay dark and not form stars somehow, which is already weird. But first, I'll actually meet to this problem with the standard model. But more importantly, the satellite galaxies are rotating like within a very thin plane for the Milky Way. So they're kind of, we have actually measured their proper motions now, so we do know they're rotating within a plane, not just within a plane. You might be thinking, well, you get disks all the time, so what was unusual here? So two major things which are unusual. First of all, the satellite plane is kind of at right angles to the disk of the Milky Way, which is oriented like horizontally. But more importantly, I think, is that the scale is very large. So the Milky Way disk is only this big, and this is much larger. So it's not really very sensible for sort of interactions between baryons like friction to operate in these extremely low density environments. It's unclear how they would settle themselves into a disk, right? So we're talking a bit more about this. So one thing you want to bear in mind is that this real image of a distant like galaxy. whereas another galaxy's kind of gone in and had its gas kind of stripped out, like behind it by tides from this, basically, right? So by this galaxy pulling on other sides differently. So yes, it's a possible formation mechanism whereby like another galaxy interacted with the Milky Way, pulled out like this tidal tail, if you like. But this is actually what it looks like, which is to say it should really be confined to a plane. Yeah, so that would lead to like a rotating system of satellites probably. But what I'll say though is, yeah, so that is possible. Like if you look at more distant systems where material is being drawn out, you can see that there's sort of forming tidal dwarf galaxies, as they're called. So they're very small, but importantly they form from material pulled out by tides. So this process is quite possible, and it happens in this system as well. You can see these clumps there. And in simulations it kind of works as well. But for the moment, we're going to leave aside this exploration because you'll see in a minute that it's going to be highly controversial if that was actually true. So we're going to see if there's other plausible explanations. So what's shown here is kind of the probability distribution of getting like the direction of the sky towards the Milky Way satellites aligned within a certain angle. So this is like sort of how closely they're actually aligned. The idea for a good theory is to get a lot of probability in this region to be aligned as well as observed, or even narrower. If you can get that happening at like more than like a 1% probability, your theory is kind of sensible. So you can see the first 8 simulations haven't really done that. They're kind of standard model simulations, nothing much happens there. No kind of interactions between galaxies. In this model, that worked very well. Maybe that had an 80% chance of working or something, because another galaxy of the same mass as the Milky Way like flew past it at quite close range. These models would work, but they involve something merging with the Milky Way, which might have destroyed or seriously damaged its disk. So maybe they're not so great. So if we do focus on that model, like what does that actually mean? The only real galaxy that could plausibly have been is the Andromeda galaxy, because there aren't any other large galaxies nearby. So if you look at Andromeda, what you see is very weird. Like you kind of see 15 galaxies out of maybe 25 in a thin plane, co-rotating about that. And the Milky Way is kind of within this plane as well. So this is quite weird. It's definitely not kind of isotropic. It's very significant statistically because these galaxies are coming towards us and these are going away. So the system is rotating within the plane as well as lying within a plane. So it kind of looks like this from the side. These going towards the Earth and these going away. Now, because Earth is within the plane of rotation, the measurements are quite accurate. They're based on radial velocities. So just to give you an idea of how unlikely these things are, if you assume that there are going to be 15 galaxies within a plane, you observe 13 of them to be rotating in the same sense. So if you call it a galaxy to be like A if it's rotating in a certain way and C if it's rotating the other way, you get a sequence of like 15 A's and C's, and the trick is to get more than 13 A's or more than 13 C's basically. So there's going to be about 30,000 sequences, and that means you're allowed this very number of A's, right? So if you just work out like the probabilities of these things, so for the case where you have 2, you have to divide by 2 at the end to account for pair double counting. But the main thing is that there's only 200 or so ways to actually do that, but there are about 30,000 sequences. So the chance of getting this is less than 1%. And that's just the chance if you already had 15 galaxies within a plane, the chance of them also be co-rotating. So clearly this isn't like a fluke of some sort, there's something to this. Now, what we actually want in a sensible like cosmological simulation in the standard model, what people want to get is a co-rotating system around Andromeda, which is thinner and wider than observed, or equivalent when it has an aspect ratio like less than the observed system. So basically that means has to be thinner and wider than observed. So anywhere in this box. Now you can see that there are some galaxies in that box, right? So this is results from a cosmological simulation. There's like 3 galaxies which kind of just were made in. One of them was actually okay, but that's out of about 8,000 galaxies. So this kind of thing is very rare. And remember that we didn't pick Andromeda because we wanted to kind of disprove Newton or anything. We picked Andromeda because it's near enough to observe properly, right? And something similar occurs around the Milky Way as well. So this is extremely unlikely. Now, so far, yeah, so that's what I was saying. So people have suggested various explanations. So in the standard model, for example, you get these filaments of dark matter crisscrossing the universe because of gravity, like pulling them together. But this is not a very good explanation because the thickness of the Milky Way, of the Andromeda plane of satellites is actually as like this line. It's as thin as this line, and it's roughly as extended. So what this means is that the filaments in the real universe are much thicker than the satellite plane. And anyway, this process of filamentary infall was already included in the simulation, so that can't be a legitimate reason. Now, another thing people noticed for the case of the Milky Way was that in these filamentary kind of models, where things do look a bit anisotropic, it also leads to a very testable prediction. The satellites should be coming towards the Milky Way. They're kind of falling in along the filaments, right? But they're actually not. They kind of want to circle orbits around the Milky Way. So for the Milky Way, at least, we know that this explanation is very unlikely to work. So far, we've only really talked about like what the dark matter is likely to do. We haven't said what happens if you include baryons. The main difference is that the dark matter can't sort of radiate and cool and kind of settle into thin disks. So obviously you're going to have a problem if you see a thin disk of the sky, right, and try and explain it with dark matter. So this is going to mean that you should think a bit about the baryons. So obviously we know baryons can settle into a disk, right? They can radiate and cool and settle into a disk, and that happens all the time in the solar system, in the Milky Way, in Andromeda. What's possible is that because Andromeda is already a disk, if you like pulled baryons out of it in a certain way, you might be able to get a thin kind of stream of material around it in a disk of some sort. So this obviously requires an interaction with another galaxy, right? But that is not a problem because interactions between galaxies are not really that rare. What would happen in this scenario? Like, why was it so controversial that this happened? We will see in a moment, but for the moment, let's just think through this scenario. The baryons will get pulled out and end up in basically the common orbital plane of the interacting galaxies. So this is good. It will be anisotropic. Obviously, some directions are preferred over others. You get a very dense tidal tail because the baryons initially had quite high density in a thin rotating disk. That in turn is because they've lost energy by radiating it away a long time ago. So galaxies can then form out of this tidal tail by gravitational collapse. Obviously, if you have a thin, dense amount of baryons, this is a thing that's likely to happen when it forms structure. So the baryons can do this, but the dark matter can't really do that because the dark matter is dynamically hot. Basically, what that means is it's like a hot gas, kind of random motion supporting it, pressure supporting it, rather than circular motion, centripetal acceleration. So the dark matter, if you kind of try and pull it out by having another galaxy near Andromeda, it'll pull it out, but it'll just go everywhere, and it'll end up really low density, and it won't be able to collapse into a galaxy, right? Because of the Jeans condition, where you need a certain density for gravity to be strong enough. So it wouldn't work with the dark matter. Now, one thing I should say, so that means when you see pictures like this, what you want to think, so everyone thinks that only the baryons are in this disk, because obviously the dark matter can't cool and settle into a disk. So the exact same argument is true for this as well, right? So just bear that in mind. you get a baryonic tidal tail, baryonic galaxies distributed basically in one plane rather than all over the sky. So the satellites can't really start with dark matter. They also can't accrete it because the dark matter's typical velocity is about half the escape speed of the parent galaxy. The escape speed of the satellites obviously is much less because they're really tiny. So the satellites can't basically either start with or accrete dark matter. So they're going to be devoid of dark matter. But they can still exist. There's no problem with them existing. So is everything alright now with this model then? So what is shown here is the mass to light ratio of the satellite galaxies in the local group against kind of their luminosity. And basically you should get numbers between 1 and 10 in this kind of reasonable range. So you shouldn't be able to get observations going all the way up here. So this suggests that there was actually a problem with the model, that the satellites can't just be made of baryons. So the high velocities that high velocity dispersions I should say, could be due to tides basically, kind of disturbing them. So they're not kind of in equilibrium internally. That's a possibility. So people try to test that by plotting so this basically shows you how disrupted the objects should be by tides. And this is kind of the limit. So what you see here, and this, on the y-axis measure the discrepancy. So 1 is good, like anything much different to 1 is a problem. So you can see here, there's two basic problems. Objects which are equally affected by tides, on the same vertical line, are either consistent or very inconsistent. So basically, objects equally affected by tides are showing, it doesn't seem to be a relevant parameter basically. But more importantly, none of them should be affected by tides anyway, because they're all maybe 10 times too small to kind of be affected by tides. And because tides scale like with the cube of radius, it means that the tides should be like subdominated by that 3 orders of magnitude. So the tides shouldn't really have been affecting the data that much, basically, is what this article showed in the context of the standard model. The other thing that could be is, so I'll just show you that in MOND what would happen is it would kind of work much better, but it would still not work with some of the faintest galaxies. So it seems to, and this obviously is the consequence of the fact that it boosts gravity in these low mass, low acceleration systems, but we'll see in a moment what happens when you redo the tide calculations for this model. So in this model, what happened is quite different, because obviously the tides work differently in different gravity theory, and you can see here basically that the objects least affected by tides more or less are in agreement with MOND. The major difference compared to the Newtonian plot is that a lot of the galaxies down here have moved across. In other words, that the objects which are inconsistent with the model, in MOND they should be much more susceptible to tides, which means in the context of this model it's entirely consistent if the theory doesn't quite work well for these objects. So more importantly, you do see this clear correlation, suggesting that tides really are the reason why the theory isn't working in this bit of the graph. Right? They should be working in here, but there they more or less are working. So one final thing that people thought was that binary stars can inflate the velocity dispersion in the lowest mass galaxies. Right? It's only a few kilometers a second. What happens there? First of all, binary stars you could kind of discover by repeated observations over different lengths in a lot of the cases, right? So what people did here is kind of plot the observed by the predicted velocity dispersion, and obviously the idea is to get 1 there. What they did then is adjust the parameters of the binary population to try and get 1 at the lowest end, because at the lowest masses the sort of intrinsic velocity dispersion is so tiny, it's kind of all dominated by binaries. So you know more or less how much binary stars there should be. So in both theories you'll see this calibration effect where they drop to 1. The important thing is that in MOND, if you've calibrated the binary population right, across the whole range, you more or less do get a ratio of 1. So the observation and the model more or less agree. Whereas in Newtonian dynamics, there's a big discrepancy across a wide range of mass. And because the mass scale is the square of the velocity dispersion, it means there's roughly 4 times as much mass in these objects as you see if you stick with the Newtonian gravity. In MOND, this obviously is consistent with just error bars, right? So in MOND it's more or less okay. The satellites therefore do actually seem to need dark matter, right, to explain it. Now what this means, of course they can't actually have had any dark matter because they're lying in these thin planes, so they have to have started in a particular way based on galactic interactions. That means that, well, we've reached internal inconsistency, right? The strong internal gravity, normally you just explain that by adding dark matter. But here we hit like a particular situation where adherents of Newtonian gravity can't just invent invisible dark matter to explain why the theory is not working. And therefore it means that the problem was actually more fundamental, that Newtonian gravity had actually failed in these objects. So it can't have been a proper description of the universe. In modified Newtonian dynamics, we get to some exciting conclusions about the local group. In particular, if you show how far apart the Milky Way and Andromeda have been as a function of time, so you get this flyby around here. So in the standard model, there is no such thing. So this is exciting. So just to show you, in the standard model, the Milky Way and Andromeda can't ever have undergone a fast close flyby. The gravity basically is not strong enough. So to try and test whether such a dramatic event had happened sort of right in our backyard, we, in a cosmic sense, we did a calculation involving what's called the local group timing argument. And so we published 2 papers about that so far. So you set up the Milky Way and Andromeda and lots of like test particles flying outwards, close to the time of the Big Bang. And you kind of let the system evolve under the gravity of the Milky Way and Andromeda and see like what happens. So the idea is to get a test particle landing exactly where an actual galaxy is, and then you can compare the velocity of the test particle against the observed velocity of the actual galaxy and see if they agree. So that's essentially what was done in this article. Yeah, the first step is relatively simple. You obtain the trajectory for the Milky Way and Andromeda. Then you get something looking like this, so the black dots are real locations of galaxies. The red dots are just like simulation particles. The arrows show their velocities. So you can see you've got like the Milky Way and Andromeda there, and the simulation traces out obviously the velocities everywhere. The important thing is we've got observations covering quite a big part of this velocity field. So near the Milky Way, particles should be coming towards us because they've kind of turned around. Farther away, they should still be going away. What's called the Hubble expansion. So if we, so if I just zoom in, you can see that a bit better. Now, if you plot like the radial velocity of all the test particles against their distance, this is the Hubble law. What happens in a smoothly expanding universe? Things moving faster, further away, and you kind of recover that at long range, right? And at short range, like basically gravity has kind of decelerated the expansion. Like really close to the Milky Way and Andromeda, you get additional like scattering type events. Yeah. So if you have close encounters with so I've already said about that. So we thought that we could actually reproduce the observations quite well if there had been no like fast Milky Way and Andromeda flyby, if Newtonian gravity had just been working fine. But if there had actually been a flyby, then obviously the model would completely fail. So what we actually, so this is basically a 1D model where it hasn't worked very well. But importantly, so the authors claim that there was actually a fair amount of scatter about the model predictions. So observations weren't agreeing very well. But what we did is Yeah, so the important thing to realize is that they don't include interactions between like all the dwarfs, but because they're quite small, that should only lead to a 15 kilometer a second model uncertainty. So this is a bit odd why that happened, but that was a 1D model. So we set about constructing a 2D model, and that should be okay because the Milky Way Andromeda orbit is nearly radial. So you construct these radial velocity maps of local group mass against the fractional rate of the Milky Way. And for example, if you knew the actual radial velocity of Andromeda was minus 110 kilometers a second, you could know that it was somewhere in this green band. In other words, you'd know like the total Milky Way Andromeda mass. You wouldn't know how it was divided up between the galaxies. But because we used other galaxies in our analysis, you could tell that. So for example, if you knew Sextans A had a radial velocity of 80 kilometers a second, you'd know that 30% of the total mass must be in our galaxy. So if you have even more galaxies, you could start to test whether the model actually works. So what we found is that it hasn't worked very well. So this is the radial velocity that's predicted in the best fit model. The observations, which are much higher, systematically much higher. So it's weird. This is actually the best fitting model we had. So just so you know, the discrepancy is about 50 or so kilometers a sec. So very high actually. So the thing is that the velocity field should be quite smooth in these regions. So it's difficult to explain what's been going on. In MOND though, because of a process I'll describe in a sec, you have a lot of these test particles like flung outwards at high speeds. And you get this really chaotic velocity field in the local group. And some of these galaxies might actually correspond to them, right? And therefore have a really high radial velocity, being therefore much more consistent with the observations. So the mechanism I was describing is what's called a gravitational slingshot encounter. So if you have a small galaxy moving like this and a heavy galaxy kind of catches up with it, in the frame of the heavy galaxy, the lighter one is approaching at 4 kilometers a second. So what will happen is it'll kind of get slingshot out at 4 kilometers a second. But the important thing is that the light galaxy, the blue one, is now moving at 5 plus 4 kilometers a second. So instead of going at 1, it's now going at 9. Okay. So that's essentially, I think that's what we see here. So this is where we plot like a histogram of the galaxies, of the difference between the model, of the observed minus the predicted radial velocity. So first of all, the blue ones correspond to galaxies which have radial velocities below the predictions. So the blue ones should trace out this kind of histogram. Now what you see there, basically if I show a 15 km per second Gaussian, it's kind of consistent. Because our model is not perfect, these galaxies are kind of consistent with our model, okay? But the red galaxies obviously are not, right? You can see that. So these galaxies, something weird has happened. And my understanding is that this peak near zero corresponds to just normal galaxies which never really went near the Milky Way or Andromeda. These ones maybe were flung out by Andromeda, and these ones maybe were flung out by the Milky Way, which is lighter and would have been moving faster. So that's what I think has been going on here. So now in MOND, what would happen is that these fast-moving galaxies should all have been at the same place at the same time, right? They should have been close to the center of the local group when the Milky Way and Andromeda flew past, because they need to have interacted with a fast-moving galaxy, and that's the only space-time location where something heavy was moving fast. So what this means is that the galaxies furthest away need to be flung out fastest to have gotten there, basically. So it's just like that. So one thing to bear in mind, you should see lots of objects which are consistent with the standard model because they weren't flung out in this way, but nonetheless some would have been. And importantly, they wouldn't just have some radial velocity, they need to follow this relation more or less. So if you actually do that, yes, remember these are net of the best fitting model, what I'm going to show on the next slide. So what's shown here is that that you have indeed a lot of galaxies close to zero. Now one thing you can do is kind of divide distances by velocities to estimate the age of the universe. So if I showed actual velocities rather than velocities minus the model, you could do that and get the age of the universe. So these galaxies were consistent with the model. This track of galaxies has an excess slope of about 40 kilometers a second for each megaparsec, which means that can be converted into an estimated time for when the flyby was, right? So what you do is you divide 1 megaparsec by 40 plus what the model is. So the model is basically uniform expansion at long range because gravity is quite weak there. So that's another 67. That means you get a flyby estimate around here. Basically what this is saying is that there needs to have been like one Big Bang to explain this, but at least locally a second kind of mini Big Bang to explain these high velocity galaxies, which was not 14 billion years ago, but probably about 9. If you just simply calculate the Milky Way Andromeda trajectory in MOND, what I've shown before, you estimate like a flyby to occur around here. This is what I was showing on the previous slide. Now another thing, the Milky Way has, so this is the structure of the Milky Way, it has this thin disk and also this like green like thick disk. And what's shown here is the velocity dispersion. The important thing is the bottom panel. So the velocity dispersion vertically to the disk of the Milky Way is a function of how old the stars are. So these stars are about 10 billion years old. These were formed like recently. So if I show what you see is this sudden jump about 9 billion years ago for stars older than that, which means, and more importantly, I managed to find out that the disk heating was stronger further from the Milky Way as well. Now what that means essentially, a sudden increase in velocity dispersion like that, vertically, what the authors say is that the velocity, the sharp increase is probably caused by a minor merger or an interaction of some sort. So it's very likely that the Milky Way really did suffer an interaction around 9 billion years ago of some sort. So if I just try and tie things together, so we had the timing argument estimate of when the Milky Way Andromeda should have flown past in MOND, and then based on the high velocity galaxies in the local group, trying to track them back in time, like rewind them, you have an estimate around there. And then if you look at the thick disk, which obviously these are quite separate considerations, right? So they all seem to suggest like the same kind of thing, that there was a major event in the Milky Way or in the local group around this kind of time. Okay, so around then, yeah. What we realize next is that if these galaxies were really flung out, they should. It's easiest to fling things out like that, sort of parallel to the direction in which the heavy galaxy is going. Okay, that way the vectors kind of add up most efficiently. So these high velocity objects should lie within a plane corresponding to whichever plane it is the Milky Way has always been moving in. It's not always been going the same way, but it's always been the same plane. So we tried to test that. So we kind of rotated like this 3D figure around a bit, and we managed to get like the high velocity galaxies kind of lining up very close to a line. They're actually not close to a line, they're actually in a plane, but you rotate it until it's edge on like that. Now obviously this is quite hard to know, is this significant? Like, we don't know yet. So we'll have to do some more statistics on things like that. So what you do is you kind of randomize directions towards the galaxies. This is what's called a Monte Carlo trial. You get the thickness of the best fitting plane each time, so you have to have an efficient plane finding procedure. And then you kind of see the observed thickness, and how many times do you get something thinner than that. So it's not actually too bad. But then there were some other considerations which came to mind, whether it was offset from the Milky Way, and whether it was orthogonal to the direction, whether the plane kind of contains Andromeda, it has to contain the Milky Way Andromeda, right, more or less. But the important thing was actually where the plane should be. So what we did here is use the fact that the Milky Way and Andromeda have satellites in planes around them and try and say, like, how did they form? Like, could the Milky Way and Andromeda have been going around in any old orbital plane and you get the satellite planes to be exactly the same? Obviously not. There has to be some, it has to depend on this a little bit. So we constructed a basic toy model where you assume the Milky Way and Andromeda exert tidal torques on each other only at the time when they have their closest approach, and only on the material on the side of each galaxy like closest to the other one. So it's kind of a simplified model of how tides would work. We're trying to do this more rigorously now. And the important thing obviously is to get the material in the Milky Way to gain angular momentum in the direction of its disk of satellites. So can you not just make the Milky Way have a polar ring of satellites, but like in the right galactic longitude, if you like. And the same for Andromeda, obviously. The other thing you need to know is that the line joining the galaxies should have rotated close to 120 degrees. So what we do on the next slide is basically, just to give you an idea, if this black line is the Milky Way Andromeda line, then the orbital pole, or the normal to the orbital plane containing them, could be like the red arrow. But it could also be like pointing this way, right? So we can't really tell which way it is. It's sort of along a great circle somewhere. That's what you can say. Now, what we did here, so the color is like how well the models kind of work. See, the blue colors mean that the models work well at reproducing the Milky Way and Andromeda satellite plane orientations. The important thing here is that we were able to obtain a tight constraint on, well, actually, which orientation is the Milky Way Andromeda orbital plane in. Answer is it's oriented like basically around here. We weren't able to constrain this tightly, but we already knew that, so that doesn't matter too much. So yeah, essentially it's this region. Now, what that means, if I show you the directions of everything I was talking about on the sky in a latitude-longitude map, so this is the orientation of the Milky Way disk, like the direction of its angular momentum, and for Andromeda. The Milky Way satellites are rotating like with the normal red arrow like there, and for Andromeda it's there. What I was showing on the last slide is that the Milky Way Andromeda orbital plane normal should be there. Importantly, the high velocity galaxies in the local group we identified, the normal to the plane containing them points in this direction. So you can see it's extremely close to where our theory suggested it would be. What we did with this blue region is kind of say, when we're doing the statistics, kind of allow anything in this blue region. Well, maybe you should have allowed like a smaller region or something, but we'll see what the results are of doing that. So was this all just a fluke? So again, you do a Monte Carlo trial where you kind of randomize directions to the high velocity galaxies. You assume that somehow they could exist in lambda CDM in the standard model, even though that's not possible to begin with. But still, you assume that they could exist. Randomize the direction, select 4 out of 5 objects, because there's an outlier there, as you might have seen. Then you kind of find out which plane is thinnest, which of these 5 combinations gives the thinnest plane, use that. You require it to be a thin plane, so only a small fraction of your trials will work. But importantly, you require the normal to the plane to point within the region I was showing on the last slide. Basically, you kind of you get an extremely small result. So just to remind you, like we basically require the normal to the mock plane normal to be in the blue region. So you could get very little. Now, so I'll just try and summarize what we've been doing then. So regarding the satellite plane issue, basically what the situation is that you observe the nearby satellite galaxies of the Milky Way and Andromeda to lie within thin planes. They're only ones you can really see well. You also observe galaxies further away like forming within tidal tails. So these things aren't controversial, but what does it mean? It means that the galaxies were formed from tidal debris because the dark matter can't rage and cool and form into thin planes. Now, what actually that in turn means is that those galaxies in thin planes should only contain baryons because the dark matter can't like radiate away and cool down like that. So then another important observation is that these galaxies also have a high internal velocity dispersion, so they need a lot of gravity to hold the stars together. But that gravity can't be provided by the dark matter, right? So what's it provided by? The answer, in my opinion, is that it has to be provided by a modification to Newtonian gravity in the relevant situation, right? On a larger scale, what we did in this article was we found local group galaxies sort of like away at rather high speeds from the Milky Way and Andromeda, but basically the speeds are so high they need to be flung out by something heavy, and obviously these are the only really heavy things in the local group, right? So they need to be moving very fast at some point in order to do that, because even if you have a very heavy object, if it's just sitting still, something light coming in will only go out to the same speed it came in. So it has to be both heavy and fast moving. You can't just have something heavy or something just fast moving. The thing is, in Newtonian gravity, the Milky Way have always been moving quite slowly. They haven't undergone a past close flyby. Now, one thing you can do, you can obviously add lots of invisible dark matter, and that will actually lead to a close flyby in the past if you add enough dark matter. But this model is unrealistic for various reasons. The most important problem with this scenario is that the galaxies would merge because the dark matter halos overlap and there's some kind of friction which is only dependent on gravity. So this line of reasoning is not right.
Or it would be severely distorted.
They would just end up merging. You would be able to see Andromeda if that happened. The issues of, so this can't be right. So this much is kind of, we know for sure this should work. So the line of logic works so far, but you can't get there, which means that you have to accept the gravity was modified again. We recently showed how even with a 3D model of the local group, it's the same logic, because you still find these high velocity galaxies, and they also still lie close to a plane. That's been winning like a prize for this work, the American Astronomical Society's one, like last May, and receiving it. So just to summarize what we're saying so far, so you need to boost Newtonian gravity in galaxies somehow. It could be by dark matter, but whatever you believe, the boost nonetheless is needed only at very low accelerations. And importantly, the amount of the boost you need is higher at smaller accelerations, which is slightly weird because it should depend on how much dark matter there is rather than on how curved space-time is at that point. So the other thing you have to realize is that this line of logic, is that this Newtonian gravity is a classical gravity theory, which may just not be right at low accelerations. Basically, So if you accept that, then you could construct a sensible model where galaxies don't have dark matter in them. If you try and focus on the local group a bit more, so here, this theory, where galaxies don't have dark matter, gravity is modified, it would imply an ancient flyby of Andromeda, because Andromeda is on an almost radial orbit with respect to the Milky Way. That's the key observation based on Hubble. If that happened, you might explain satellite galaxies lying in thin planes as kind of remnants from this interaction, and also the internal dynamics. It might also even explain why some distant local group galaxies are flying out at high speeds. So that's what we were showing in this recently submitted work. The reason is that these distant galaxies prefer to lie within a plane, which could well correspond to the Milky Way Andromeda orbital plane. If that was actually true, then the orientation of these galaxies, of the plane fitting them, is about right to explain the satellite planes of the Milky Way and Andromeda, which are much nearer, at least using the toy model we've constructed so far. I guess I'll just leave it there and see if you have any questions.
Thank you very much. See the circle masses. It's fascinating stuff, and I think What I would comment perhaps is that the whole history of science and astronomy in particular has been of things changing from Ptolemaic ideas to Copernican, and then the advance of Newtonian gravity and then Einstein. So it's entirely possible, in fact it's almost certain, that Einstein's theory is not the be-all and end-all of everything. So yeah, we can see that there are certainly...
Standing on the shoulders of giants springs to mind.
Yes. Yeah, there's certainly a lot of interesting stuff to digest there, especially that so many of the things tie together so well,
yeah.
and that you can see certain discrepancies in the classical models, which, you know, there are some interesting correlations that I think I'll have to do a lot more reading on this. It's not a subject I've spent a lot of time looking at, but I think I will.
Can't understand why.
No, that's just the amount of time I have available to read stuff. So I'll stop writing.
I was fascinated by this mass to light ratio.
Yeah.
Does that mean that in the age of the galaxy would be a function there because of the types of stars that we've got? You know, in old galaxies we've got metal-rich stars. In young galaxies we've got predominantly hydrogen, deuterium, and that. Does that mean that the light to mass ratio would vary?
It does vary by with age of the galaxy, but what you have to realize is that at the same time as the mass to light ratio of the galaxy is changing with age, its color is also changing, which is why if you knew the color you could estimate the mass to light ratio. As for what you're trying to raise maybe about stellar remnants, like of things like black holes and neutron stars, we basically make a reasonable allowance for these things in the modeling, because in the very close to the sun you could actually see all these really faint things and know roughly how much there is compared to the light.
Yeah, and something else that crossed my mind when you said mass to light. I was assuming that light meant all electromagnetic radiation, but
Not just the visible bit.
No, actually,
when you said the colour, I thought, wait a minute.
the crucial thing is actually in the near infrared, because this is where the mass to light ratio of stars is less dependent on things like age or the,
Right.
basically.
Yeah, yeah.
But yeah, it is meant to be not just the visible.
Any other questions?
We daren't.
No.
Just very briefly, I don't know whether I've understood, well, I know that I haven't understood that, but what you were saying, I think at the start, was we don't know what dark matter is.
Yeah.
And then you
Or
went
whether it
on...
exists.
Sorry?
Or whether it exists, right?
Yeah, well, yes. And then you went on to say that the models of dark matter were accurate, and how the heck can you say it's accurate if you don't even know what the damn stuff is?
Whether it exists.
Or whether it exists.
Well, what I meant by that was that it shouldn't have been substantially affected by the baryons, because in the context of the dark matter model, the baryons should be making up a very small fraction of the mass. So whatever the baryons were doing shouldn't have mattered too much. As for the dark matter, yeah, you are right that it can matter a little bit whether it has additional non-gravitational interactions, but we think that would cause substantial problems with structure formation in the model. And essentially, if you're going to have, and also you have to understand we haven't detected it either, which means that it can't really have very strong non-gravitational interactions, right? You also don't, not just with ordinary matter, but with itself as well. Because if it did, then you would be able to see sort of gamma rays coming from the nearby Milky Way satellites chock full of dark matter. So we know that dark matter, if it existed, would be basically primarily interacting with itself gravitationally. And also that the baryons would make up a very small fraction of the mass compared to the dark matter in some galaxies. And in those galaxies, that's why we expect that our models could be quite accurate. That we could model the paradigm accurately. Whether the paradigm is right or not is another issue.
I don't know whether you know the local expression around here that fair makes your heat nip.
I think I could have to work on that. Makes your brain hurt.
David, from a practical point of view, a flyby of the Andromeda Galaxy, I think it would not be a very close flyby.
Well, that's what we're trying to work out now. We think it would have been about sort of 20 kiloparsecs, about 60, 70,000 light years. It would need to be reasonably close to actually do anything, but
How close would it be to-
that's what we think at the moment.
Well, there was obviously a point at which if they come
Yes, yes.
closer than a certain point, then you will get
Then you will get friction and they'll start to merge.
serious distortions.
So Andromeda scale length is about 5 kiloparsecs, so it goes at about 5 or 10 kilo scale lengths maybe, so maybe 30 kiloparsec or something. So, but because of the inclinations, that Milky might not have gone through Andromeda. It might have
They just have sort of orbited around each other.
yeah, kind of.
Interesting. Anyone else? No, I think we're all ready for a cup of tea. So thank you very much again, Indranil.